Our next section is about safe intervention, and it's going to be moderated by António Costa. António is an associate professor of the University of Minho, the Department of Informatics, and he's also a partner of the InfraROB project, and he will be leading us in this section.
Thank you, Noemi. Good afternoon, everyone. Welcome to this section 6, titled Safe Interventions. This session is focused on the results achieved by OMICRON and InfraROB on enhancing safety on road intervention using cutting-edge technologies like AI, UAVs, V2X communications, in order to achieve enhanced perception, generate alerts, especially when considering robotized interventions. The session has 3 presentations. The last one is split by 2 presenters. The first speaker is Professor Joaquín Martínez Sánchez from University of Vigo, Spain. Joaquín is Scientific Coordinator of InfraROB. He's an assistant professor at the University of Vigo, where he also gained the degree in telecommunications engineering with a specialization in electronics and a PhD doctor in Europeus in environment technology. He is the principal investigator in HERON Road to Win both national projects with a focus on digital twin technologies for infrastructure management and aim to improve infrastructure maintenance with autonomous robotized solutions. In InfraROB, Joaquín focused on enhancing road maintenance safety through the innovative monitoring system based on AI analysis and UAV and small robots collaboration. The second speaker is Martin Rivas from Indra. Martin has an MSc in civil engineering with over 6 years of professional experience. He serves as a researcher and project manager within the innovation team of Indra's mobility unit. His expertise spans intelligent transport systems and construction innovation. In the realm of construction, Martin supports the digital transformation of the sector through Indra's engineering subsidiary, ProIntech. His involvement includes managing innovative projects such as OMICRON, aiming to modernize engineering process and infrastructure management. For last presentation, we have Dr. Rod Adjen from IMC. Dr. Rod Adjen is the co-founder and president of the firm Infrastructure Management Consultants. After receiving his doctorate in 1999 in ETH Zurich, he was employed by AMKH and Berger AG before founding the firm Dr. J. Grobe and Partner, which specialized in engineering structures construction, structural safety, and computer-aided engineering solutions. In 2001, Dr. Adjen became a visiting professor of infrastructure management at the University of Pennsylvania in USA. In the InfraROB project, Rate has been leading the work package 4 on management systems, upgrading, and safer operations and maintenance. Finally, last but not least, Leonard Hoffman from ASFINAG. Leonard Hoffman studied physics with a graduate degree from Ludwig Maximilians University in Munich, Germany, and a PhD degree in solid-state electronics from the Technical University of Vienna in Austria. Before joining the ASFINAG in 2020, Hoffman was working in research and development in various industry sectors and has become a certified professional in the field of requirements engineering, CPRA advanced level. In the ETS service department of ASFINAG, he focused on RID projects in cooperative, connected, and automated driving and digital infrastructure. In the InfraROB project, Leonard was responsible and played a key role in the many demonstration activities in Spielfeld, Austria, particularly the use case related to enhanced safety with using wireless V2X communications. I now welcome the first speaker, Joaquín Martínez.
Good afternoon, everyone, and thank you for having me. Thank you for the presentation. This first presentation is related to the technological area 4 of the InfraROB project. That is the remote pilot system for safety. In the structure of this presentation, we will cover the description of the system, the overview, what are the main results and outcomes of the system, and we start just describing the objectives of our system. And despite all the efforts, maintenance works are still one of the most risky activities in the construction sector and in road traffic. If we take a look to the statistics, we can see that this is a problem more around Europe. And if we go to the key factors for this problem, we find that the speed and the distraction of the drivers. So our objective is to promote a new collaborative operation of different remote pilot systems, aerial and ground, just to alert the users of the road and the drivers that are approaching to the work zone. If we take a look at the system overview, the design consists of two use cases. The first one is the monitoring of the work zone itself, the monitoring of both the personnel that is working and all the machines and robots that are inside this work zone. And the second use case is for doing the tracking of the vehicles that are approaching to this work zone. So capturing both the two key factors that we described before, the speed and the distractions. In taking a look at the remote pilot aerial system, these systems based on quadricopters or general multicopters have a limited autonomy for this task because the typical autonomy runs from some minutes to half an hour perhaps. So we need to have an extended operation of these kind of systems that are going to be the basis for the asset localization inside the work zone. So using this localization, we can assist the deployment of the remote pilot that are based off the ground system, that are these safety cones robots. All these elements are managed with a software system that is based on artificial intelligence. The other vertical of this project consists of the remote pilot ground system that takes care of this part of the distraction by alerting the users and the vehicles when there's a car that is approaching too fast or there's some problem with the location of the machines inside the work zone. So we have these remote pilot safety cones and the software that's doing the orchestration of all the systems, both aerial and ground systems. So this software has an interface with communication capabilities to the other partners in the project and to the infrastructure. So what are the results of our system? We start with the research outputs. We did a system integration in a commercial drone of all these elements. The tethering system that permits the extended operation, so we extend the operation to several hours. We can do the monitoring of the works during the workday, so we can have 4, 6, 8 hours of operation compared to the 30 minutes of a standard operation of a quadcopter. We included in this commercial system a GPU-based system to do the analysis based on artificial intelligence of the images. And even if it may see that it's not complex because we have only a system that is hovering on a steady point, we have to manage with all the regulations for aerial systems and in drones in general. That is a challenge thing. Regarding the real-time detection and tracking system, we have improvements both in the two elements of the system. In the radio, we have 90 frames per second of the analysis, so we have a faster operation in the performance of the AI tools, and this gives us some room to improve the resolution of the images that we are going to use. So we can have a higher resolution than the other competitors or the other systems that are doing this. So if without optimized pipeline, we also have a better estimation of the hyperparameters that we use for the training and the test of the neural networks. This accuracy permits us to have the calculation of safety surrogate measures in real time also, and these safety surrogate measures are the base for the safety analysis that then rise the alerts to the vehicles. Not only capturing the speed of the vehicles, but some other parameters like the time to collision and the drag SSM. And last but not least, we have developed a system orchestration that makes the collaboration between all these systems all together. This GeoCore software has the capability to communicate to the other partners on the project and communicate to the roadside unit that some other partners used to communicate to the infrastructure, and from the infrastructure to the vehicles that have this capability. So if we take a look to the main outcomes as a conclusion for this project, we improve safety on the reducing the workers' exposure to live traffic, and with 3 pillars. These 3 pillars are the remote pilot area system that we have with artificial intelligence capabilities to perform the tracking of the vehicles with a high accuracy, the extended autonomy of this remote pilot system with Tetris solutions to have several hours of operation, and our software developed customly to do the orchestration of all these elements. And finally, to finalize, we have the future trends for this software, mainly and remote pilot systems. The first is just improve the TRL of the system to go to the market, or at least to have a more robust solution. Second, the application to other mobility services like smart cities. And finally, to deepen the integration of simulation software, just to improve the capabilities of the system to predict conflicts in the road, and then have a measure to try to avoid these conflicts that would cause, for example, road crashes. So thank you for your attention.
And then I'll call Martin from Indra.
Good afternoon, everyone. My name is Martin Rivas. I'm from Indra. I'm going to present today our V2X communications and road safety technologies. So what we mean when we call V2X communication, this is a technology that allows the vehicles and infrastructure to communicate, to exchange information regarding all the incidents and events that could happen on the road. In this case, we can coordinate our actions to improve the efficiency and safety in these roads. And also we are paving the development of the future autonomous mobility. So we have 2 main channels of communication for deploying this technology. We have the ITSG5 short-range communication that is deployed through the RSUs. And also we have the typical mobile technology through 4G, 5G that has more coverage. So regarding our cooperative information transport system architecture, in this case, within this project OMICRON, we deploy infrastructure to vehicles communication. So we will have our control center when we integrate our sources of information regarding all the traffic data, weather information, other general information from different authorities and operators. This information we transform it to a standardized format that is called the CITS services, and as you see, we can provide these different services regarding a maintenance vehicle that is approaching to a specific point, a roadworks warning, weather condition, smart routing, etc. So these services are sent into the RSUs, the roadside units. These are the antennas that we place on the road that can communicate with the vehicles, and these vehicles receive the information in their onboard units, in their laptops, their smartphones, etc. So, to put in context all the equipment that we will need to deploy these systems, we have our roadside units, these antennas that we place as high as possible in light poles, in gantries. Then we have our control center, when we have our digital environment, we see where is placed this RSU and where and what are the services that we want to provide. The onboard unit that is placed in our connected vehicle, and then our human-machine interface, our visualization, I would say, that can be on a smartphone, through a visualization app in a tablet, etc. In the future, this would be in the typical screen that we have in the vehicles. So, in the context of OMICRON project, we performed 2 different tests. The first one was in the A2 highway in Guadalajara, together with our colleagues from Acciona Concesiones. We installed one RSU there, and also we bring one connected vehicle. We obtain information from the Acciona maintenance service. They provide us the typical roadworks that they had on the road, and with this information we could create a roadworks warning that we send this to the vehicle. So I don't know, no, how can I put this video? There are 2 videos. This one, we can see how we receive the information in our tablet, and the other one, we receive the information as we enter in the range of the RSU. We receive this notification in our smartphone, and as soon as we cross the RSU, the incident in this case, the message disappears. Regarding the second test, the final test performed in Florence, together with Autostrada per l'Italia, we deploy also one RSU. Also, we bring one connected vehicle, and in this case, also we create a roadworks warning and visualize this information in 2 environments, in a smartphone and also in a tablet. So in this case, this is another video. And as soon as we reach this range of the RSU, we receive the notification in our mobile phone. And as soon as we cross the incident, in this case it was a simulated incident, the message disappears. So, as a final results and conclusions, we could say that we enhance our detection distance. In the section where we place these RSUs, we can increase in receiving this real-time information in 2 minutes. Also, we reduce this traffic disturbance, so the vehicles can maneuver, change the lane, reduce their speed, or modify their routes after receiving this information. And also, we expanded the sources of real-time information, despite the typical ones that we have all in our smartphones, or the typical public authorities information. We can provide this from the operators of the road. So we can say that this V2X enhances safety during the maintenance by providing real-time updates, enabling seamless communication among stakeholders, and offering also an scalable solution based on connected vehicles adoption. So this is it from my side. Thank you very much.
I now welcome Rad and Leonard for the last presentation.
So, good afternoon, everybody. I don't know whether you're aware that outside is a beautiful blue sky and the sunshine, and we are sitting here windowless room. So, I hope that there's on bright side you have seen today something about what we are doing here in InfraROB and OMICRON, and I hope as well that I'm not going to disappoint your expectations. Now, the first part of this presentation I'm going to give you, and we are here, as you probably have seen already, this path. These are some of the technological activities or the technological areas that we had in InfraROB, and we are moving here to technological area 5, and it's underscored here that we are going to talk about the safety of the work zone. So in order to get a bit of hold of this safety in work zone, there are some things that should be done first, and that is that we have to figure out how to communicate between the workers, between the vehicles passing the work zone, and also vehicle within the work zone. So they have to develop the methodology to incorporate robots in this environment. So we assume that there are some communication already there without the robots, and then we are going to put the robots into it and see what's going on with regard to that. For that purpose, we need to, of course, as you already heard, to track maintenance robots and machines, but we don't really know what's going to happen with robots because robots are not being used today. So this purpose, we need to simulate a bit. And, you know, if you don't know what's going to happen, you have to simulate and try to figure out whether there is some difference between simulations of that what we already know. And this is actually the maintenance actions without robots, and the one that we don't know, there's a maintenance action with robots. And this is actually one of the things that we did with the agent-based simulation of the work zone, and in order to get up what is the difference between these two. So this is here a big picture. You don't need to read that, what is here. There are two things, however, that are quite significant here. One is that this communication pattern here is actually telling you how the different actors are communicating with each other. You're going to hear that from Leonard in much more detail. These are on the right-hand side, back down, you have seen that there is the drone that you already heard. There is onboard units, there are the vehicles, and they communicate with each other. One thing that I would like to emphasize here is that the upper part in the gray area is actually plugged into the existing ITS system of ASFINAG, which is kind of a nice feature as well. So, what is happening on the ground? You know, if everybody would behave nicely, we wouldn't have any kind of communication, but people don't behave nicely, and in some cases that bad things happen. So what we did here, for different measures, all of the maintenance sections that you heard about, the small robots and also the potholes, and also for the large maintenance section, we actually simulated the activities on the ground, and these are here presented. You have a nice now pattern how the vehicles are moving. Of course, we are taking some data from the drones. And you see also down there how the workers and the machines are moving within a work zone. So this is everything nice here, but it's not always like that. In some cases, something like that happens, you know. So here you see that this red vehicle jumps into the work zone, and this is what we regard the accident. So we did quite a lot of Monte Carlo simulation for that in order to figure out whether there is any benefit from robots, right? And this is what we did in this particular case. So the baseline, without robots, we already knew a bit, we could calibrate it kind of nicely. And then the second part is we did with the robots what is going on there. So you can see here, and this is one thing that is here highlighted in a red box, that there is a significant reduction of the fatalities and injuries when you use robots here. And this is roughly about 25%, if you can see in this diagram. And this is the effect that we are expecting if we start really using robots in the future to the same extent. Now, there's also think about that, whether this whole communication would function nicely. And these are latency issues, there are issues of the moving traffic and so on. So there was also a second simulation which was taken care of by Minho, and this is here presented in which we did multiple simulation in order to figure out whether the time to inform workers and also the vehicles is sufficient enough to prevent some kind of the bad thing happenings. And this is something that has been done with this simulation that is presented in this diagram here. So the overview of simulation here is presented in this slide. You see here there are a cone there that already presented before. There is a drone which is also giving information there. There is a roadside unit, and there is also the onboard units, and we also assume that the workers would have onboard units which are going to tell them if something bad could happen to them. So with that overview, I give to Leonard. He is going to give you some further information.
Thank you, Rade. Yeah, good afternoon, everyone. From a road operator point of view, the safety is crucial. So we've heard that several times today. Safety incidents are important not to have, especially Like there are things which people see, but there's lots of stuff which is beyond human perception, and there technology can help. So if we talk about CITS can do a lot about safety. So I'm happy about the nice introduction to V2X from Martin. If we have a cooperative ecosystem, we know more about safety incidents, we get them faster, we get safety relevant information where required, because the instances are connected, so we're talking about connectivity here, and also we have the chance to increase awareness of the work personnel as well as the traffic participants. So this is something we looked at very deeply in InfraROB, and did some demonstrations there, and I will present the results to you. So the CITS-based use cases, so all of these things which are connected, you've heard before. There are 4 major use cases. One is the roadworks warning. I'll come to all those later in detail. One is the roadworks warning, which is in fact productive at ASFINAG. One is a speeding vehicle. You've heard about this before as well. When the vehicle has dangerous movement, too fast, and it moves into the work zone, there CITS can help. We have a person on the road, which means that a worker does not pay enough attention. He gets too close to live traffic. And we're talking about the deviating machine in the next slides. So that means that if you have more and more automation on a construction site, then it could happen that machine has a wrong behavior, and of course everyone should be involved to see and aware that something is not okay. So we did this all in Spielfeld, Austria, in the south of Austria. We used those portable devices there, as you see in the image. They're also outside. We have a demonstration, so for those of you who still would like to have a look at those devices and see some demo, just stop by. And what we also had on the site, Rada was also talking about all these items there, so the drone, the cone, processing unit, and so on. So we had it all in a quite rugged box, with some industrial PC and then the roadside unit and access points, and we installed that in Spielfeld. And then we had the chance to do some tests there, some demonstrations. So the first one, as I said, the car approaching, it's nothing special. It just needs to know, okay, there's a roadworks warning ahead, which means I have to reduce my speed, I have to pay more attention, maybe change the lane. This is something which is productive. And as it is productive, we are sitting in a Volkswagen, and it's a Golf 8, and we're just approaching the roadworks. So the video starts, and what is important here is in the cockpit, you'll see some message. In this case, it's in German. It says construction site ahead. Sorry, I was maybe not loud enough. So there was in the cockpit, it was a message saying construction site ahead in German, and you just, you get the information as early as required, and then you can increase safety. So this is something we did in InfraROB as well, although it is a live service in Austria. The next thing is a speeding vehicle. This was developed within the project. So what does it mean? It means we have a drone. It means we have information that a vehicle is on a wrong track. And what we do then is we can give these portable CITS devices to the workers. Maybe you know one of these workers. He sits in the audience. And when then a car is approaching, of course, we set the threshold rather low. I mean, we are not, we didn't go too fast on the highway. But there you see the, oh sorry, it's not working. Sorry, yeah. So you see the Volkswagen approaching, and the Volkswagen also sends out CITS messages, so we know where it is. And if it gets too fast, we get this special message saying speeding vehicle, and everyone is warned. This is the corresponding icon. And the third use case is the exposed worker. So if a worker gets too close to the live traffic, everyone should be aware. And this is not productive, so we again sit in the same car, but we have the portable devices now shown additionally. And on the top right-hand side, you see the other perspective. So those videos are synchronized. and you see that the worker wearing such a portable device now gets very close to live traffic, and a message appears. So there he comes, and we detect his position because he wears that device, and we see then person on the road, and the driver gets warned. And last but not least, it's the deviating machine I was talking about. So this connects to the automated paver, which was developed in the InfraROB project. And what we did there, again, we have this portable device, and we put another portable device to a roller, and we defined a rectangle, which is a area which is allowed for the roller. And as soon as the roller leaves that area, we get a deviating machine message. There you see it. It's all dedicated short range. It's all within the CITS ecosystem. So these devices can help us to increase safety, to make everyone aware if things go wrong, track positions of machinery, and so on. So that's it for the demonstrations we had in Spielfeld. What's next? So one thing is for more enhancements in that field, we should have better and more accurate and more structured accident data, so as basis for calibrations, for simulations, so that we can proceed there, what Rade said. Then we need further testing in various environments. I mean, this was a proof of concept, but of course there are different weather conditions and different types of roadworks. Then standardization is a topic. We've heard about it before. Some things are standardized, but those new messages, like the deviating machine and the speeding vehicle, have not been standardized yet. So this is the path to follow. And last but not least, these products, you've seen them, they're meant to be in a bus, in public transportation, so that you get green light. So we just took them and used them completely different, had big battery packs with them, and of course we need some product enhancements so that workers are really helped there. That's it from my side. Thank you very much.